section. So today I'm extremely happy to announce that we have among us our Dr. Ahmad Zubair, who was previously a young professional member of our section, and then he moved to United States. He's going to give his talk on wideband semiconductor devices for high power and high frequency electronics. So Dr. Ahmad Zubair completed his B.Sc Engineering from Bangladesh University of Engineering and Technology Department of EEE. And there he was the top of his class when he graduated. And then he served as a lecturer of the same university. Then he completed his PhD in EECS from the Massachusetts Institute of Technology, or MIT. And he's currently working as a postdoctoral associate in MIT's Microsystems Technology Laboratory. So today I'm very happy to introduce him, and let's hear from Dr. Zubair regarding his talk.
Thank you, Sajid Bhai, for the nice introduction. Can you hear me?
Yes, we can. Thank you.
Okay. Yeah, thank you for the invitation and the nice introduction. I'm very glad to be back in a IEEE session here. I think it's probably at least 4 or 5 years last time I did a talk with the IEEE Bangladesh section. I'm really proud to be here. So today I'm going to talk about my current research focus on the wide bandgap semiconductor devices. Before I start, Sajid already told that I was a graduate of the department from EEE in February 2011. Then I served as a lecturer for 1.5 years before I started my PhD in fall 2012 in MIT EECS. In MIT, first I did my SM, which is equivalent to the master's degree in MIT in August 2014, and finally finished my PhD in EECS under Professor Thomas Palacios and Millie Dresselhaus in June 2019. In PhD, my research focus was nanomaterials, particularly two-dimensional atomically thin layered materials and their application into electronics. After PhD, I actually switched a gear a little bit and changed my focus into a high power and high frequency semiconductor devices, where I'm working now as today. So this talk, I'll mostly talk about my current research focus, and at the end, I'll try to give a brief glimpse of what I was doing in my PhD too. And feel free to ask questions and yeah, any comments. So to start the talk, I'll first try to motivate why we need the wide bandgap semiconductor materials for particular two applications. First is high power electronics, and the second is high power and high frequency electronics. And after motivating the need for these wide bandgap semiconductors, I'll try to give 3 specific examples of a particular wide bandgap semiconductor, which is gallium nitride. I'll talk about the gallium nitride lateral HEMTs and give a brief example of the gallium nitride vertical power FinFET. And I'll introduce the gallium nitride hot electron transistors. And I'll end my talk with an outlook that what's next in the future for us in this application space. So what are the application space of power electronics? So the way power electronics is being defined is basically the voltage and the current rating of the devices. So here I have a plot on the axis. I have the voltage rating of different application space and current rating of the same application spaces. So as we can see here that for power electronics, the voltage rating of the operation of the device can extend from 100 volt to nearly 10,000 volt and the current rating of the devices can extend from 0.1 amps to more than close to 10 kiloamps. So this is a very wide range of the power that these devices or this application spaces operate. So just to compare why this needs a different kind of electronics, why can't we just use what we use for microprocessor, just silicon technology, why we can't use that? Just to compare the numbers, this is on the right side, we have the famous plot of number of 40 years of microprocessor trained data. So we have here number of logic cores, the number of transistor in a microprocessor in this yellow dotted lines, where we're showing where now we are dealing with the billions of transistors in the device. I'd like to bring attention to one particular curve, which is the one here, what's called the typical power in watts. So if you look here, as of today, or 5 years ago, this plot is quite old, the power in a typical microprocessor was about 100 watts. Although the power density is extremely high, the total power the microprocessor has to deal with the billions of transistors is actually only 100 watts. And now if you go back to the left-hand side of the plot, you see this dotted line. This is where the 100-watt lines looks like. So as we can see, the application for power electronics is actually deals with them than the typical microprocessor that we are, which means that we cannot use this, the same technology for as the building blocks for power electronic devices, but we have been using in the microprocessor or the consumer electronics. So these examples here on the left is from a book of Professor Jayant Balika from 2008. So which is basically very old compared to how the field is changing. But there are also new emerging applications. For example, we have the electric vehicles, where we have a lot of the electric vehicles and other automobiles where we have a lot of electronics on board, like converter, onboard charger, battery, even Tesla, including inverter with silicon carbide module these days. And there is a market projection that in US dollar, the power electronics market is rising from very exponential fashion. One new application space. Another application space is the data center. In a data center, when the AC power comes in, it goes through many converters and the power electronic stages in different voltage levels. So with the rise of this new to emerging field, the automobile applications and the data center, the demand for power electronics is now exponentially increasing. And these application spaces are pretty new and comes with new challenges that the existing power electronics, which is mostly based on silicon devices, cannot fulfill. So another key figure is actually I'm showing here. This is from Lawrence Livermore National Lab. They publish this energy flow chart in the US every year. So I'd like to focus on just on the top where we're in this part where we're talking about the electricity generation. So here the units are quads. So in US in 2019, the electricity generation was 13 quads. And if you look at the usage of electrical energy from the generated energy, only 12 quad was used in residential, commercial, industrial, and transportation. But another 24.2 quads was rejected or wasted. And most of this rejection or wastage happens actually the inefficiency of the power electronics, what's used in this path of the power flow. So that's also a motivation why we need to make our power electronic devices better. And to solve the problems, what we focus is mostly in the device level. We want to make a better device to increase the energy efficiency. And as a result, we also can save the climate by reducing the carbon footprint. So now I'll talk about what kind of devices we use for power electronics. On the left, we have our standard logic MOSFET. And in a MOSFET, we have 3 terminals. We have source, gate, and drain. And we have a channel between source and drain where we apply a gate bias. And when we have a gate bias larger than the threshold voltage, a channel forms and the current flows. So this is a pretty standard what logic devices looks like in our microprocessor and any regular day-to-day low voltage applications. So the key feature of this device is a symmetric device, which means we can, if there is no body connection, we can swap the source and drain. And it's pretty symmetric compared to if you look from the gate, from our source or drain. In the typical application, the voltage we apply at drain is typically the same as the voltage at the gate. And the relevant parameters we talk about this logic MOSFET is the threshold voltage, the on current, off current, or subthreshold swing. Now, if we try to look into a so-called power MOSFET, structure is very different. It's a MOSFET, so we still have a source and drain and a gated region. But what makes it really different is basically first the structure is typically the power MOSFETs are vertical structure, which means the source and drain are in different plane. If you compare against the standard logic MOSFET where the source and drain in the same plane on the surface of the substrate. Another additional parameter that comes into play is basically so-called the drift region here. So we have, after source, we have this channel region here, and then we have an additional drift region that helps us to maintain the high power application of the device, which I'm going to explain the next slide. So if you look at the typical characteristics, very idealized typical characteristics of power MOSFET, it should look like something like this. On the x-axis, we have the applied voltage in the drain, and the y-axis, we have the drain current. And when the device is off, which means if you apply a very low or zero gate voltage, there is no current flowing through it. So now if we start increasing the gate bias, we start seeing current, and we see the saturating characteristics, which is the active region, and the linear region, where if you take the slope, we'll get an on resistance. So there are two parameters we are primarily concerned about when we're using the MOSFETs in power electronic application. First is the on resistance or the slope of this curve, which determines the resistive loss of the device. So our goal is to minimize this on resistance. And the second parameter, which is historically called BV or blocking voltage, it's defined here. So when we have no gate bias or negative gate bias, there shouldn't be any current flow through the transistor because there shouldn't be any channel forming in the device. Then if we keep applying the drain voltage, at some point, for example, here marked as BV, the device will start to break and it shows significant current conduction here. This particular voltage where the applied gate voltage is 0 and the applied drain bias where the device starts to break, that's called the blocking voltage, which determines the off-state blocking capability. So primarily for power electronics application, a power MOSFET is benchmarked against these two quantities, the on resistance and the blocking voltage. So in this slide, I'll try to talk about how do we decide what kind of drift region we're going to use. Again, on the left, we have our cross-section of a power MOSFET. And for drift region is mainly to determine the blocking voltage. And as I just discussed in the previous slide, to determine the blocking voltage, the gate is set as 0 volt. So we can consider this is practically a diode. So we simplify this device as still as a diode. So there is no influence of the gate. And what's different in this diode is it's a standard diode here with a resistive region or drift region, which is shown in the equivalent circuit as the RD. So how do we design this RD and what are the factors should we consider? That's the question we're trying to answer here. So to remind you, in this structure, the drain side is the N-type region, and here we have a P-type region. So if we apply a positive bias at the drain, that means this device will go into this diode will go into the reverse bias. And for the simplicity, we assume that this doping of the P-type region is very high. And if you try to plot the electric field across the vertical direction, it will look something like this. The channel will start to deplete, and we'll see a linear electric field because the doping is assumed uniform. And there will be a peak electric field at the interface of the drift region and the anode. The doping of the p-type region is. So, as I just mentioned, the BV is the applied voltage where the devices start to break. How do we know that when its devices start? The way we define is when this peak electric field reaches the critical electric field of this material, of the drift region. So this critical electric field is a material parameter and it's a constant. We cannot change it for a given material for particular dope. So if we need a larger blocking voltage, what should we do? So BV is just a voltage, so we can calculate BV as a EC, which is the critical electric field, times the thickness of the drift. So it's a natural to think about if we need a larger blocking voltage, why don't, and EC, we know there's a material constant, why don't we just increase the thickness of the drift? But here comes the trade-off. So if you want to calculate the resistance of this region, we can just use the first principle of resistance formula from our properties of material course. R1 would be L over A by sigma. Now, if we calculate the resistance per unit area and take the relevant parameters into the account, we will see that the R1, which is called typically is called specific on resistance or R1SP, is turns out to be this equation: the function of the depletion width or the drift region width, doping of the drift region, and the mobility of the carrier. In this case, it's electron. So if you do some simple math, which is shown in this book here, and what we end up with is basically the figure of merit of a power MOSFET for the drift region, this equation, which is called the Baliga figure of merit. So this is a ratio of the specific on resistance over the blocking voltage square. And as we can see from the right-hand side of the equation, this is a function of only the material parameters, the dielectric constant, mobility, and the critical electric field. And the goal, our goal is basically to minimize this figure of merit on the left-hand side. So we need to minimize the resistance, to minimize the switching loss, and increase the blocking voltage for a particular application. So now, in the market, most of the power electronic devices or the semiconductor devices are based on the silicon technology. We use silicon MOSFETs for almost all kind of application, mostly because of its availability and the economy. So now on this, here I tried to plot this figure of merit I just discussed in the previous slide. On the x-axis, we have the blocking voltage in megavolt per centimeter. And the y-axis, we have the specific on resistance at milliohms per centimeter square. And if we take the parameters from silicon, from the literature, and try to plot, we'll get a curve like this. And just to remind you, our goal is to move to this corner on the bottom right, where we have a highest possible blocking voltage and lowest possible the on resistance. So this clearly shows that the application of the silicon transistor, just from material point of view, is very limited below 1000 volt and in this range. We cannot cross beyond this line by material parameter limitation. So what if we try to replace this silicon with another semiconductor that has a wider band gap? Take, for example, two popular wide bandgap semiconductor, which is silicon carbide, which has a energy bandgap of 3.2 electron volt, and gallium nitride, which is a energy bandgap of. So what happens in semiconductor, if we increase the energy bandgap, the critical electric field where the semiconductor breaks down is also increases. So in silicon, we have the critical electric field of 0.3, but in silicon carbide and gallium nitride, we have 2.2 and 3.3. And if you look at this equation here right now, so we can assume that because of a cube dependence here on the critical field, for the if we plot the silicon carbide and gallium nitride figure of merit in the same plot, we see that we should expect a much larger improvement in terms of this power electronics operation. Pick some numbers. If we keep our specific on resistance constant and with the same thickness of the device, for gallium nitride, we can get more than 50 times higher blocking voltage. And for a fixed blocking voltage, we can get a 3000 times lower specific on resistance just by changing materials from silicon to gallium nitride. This is very exciting that if we can just move to a material with a higher band gap or wider band gap, we can enhance the application space of this power electronics material and can enable many new applications that was not possible before. Now, let's look at the second part of the application space where we just don't deal with the high power, we also deal with high power and high frequency. So here we have a typical schematic of a high frequency MOSFET. In a typical high frequency MOSFETs are a lateral transistor where source and drain are the same plane. We have the gate here. The channel length is defined by LG, and we have this region defined by. So if you want to operate a MOSFET in a higher frequency, we need to minimize the carrier transit time between source to drain. So from simple physics, we can define the carrier transit time by the distance traveled, which is LDS, distance between source and drain, times the average velocity of the carrier in this channel. So now, if you want to minimize this transit time or increase the frequency, we can define for the tau min, which is for a fixed length is LDS. The maximum velocity a carrier can achieve in the channel is the saturation velocity of the material, which is again a fixed material parameter. So this is the minimum velocity we can achieve for a particular given channel length. So now this works only for the higher frequency. But now if you want to add high power into the equation, we also think about the blocking voltage, how much blocking voltage this transistor can provide. And we want to apply as high voltage as possible. So again, we go back to our old equation. The maximum VDS that we can apply would be limited by the critical electric field of the material and times the distance between source and drain. Here we can see that trade-off here. So if you want to minimize the transit time to go for higher frequency, we want to minimize this LDS. LDS is constant. Now, if you are also increase the power capability or voltage capability of the device, we want to increase the LDS. So there is a trade-off. High, we can go with the power when a device is operating at a higher frequency. So to deal with this dilemma, in 70s, there was a seminal paper from E.O. Johnson, where he defined a figure of merit, which is famously known as Johnson's figure of merit. Is the maximum unity current gain frequency of the transistor times maximum voltage that can be applied. And it turns out to be defined by a material constant like EC, which is the critical electric field, and the saturation velocity of the carrier. And this is to evaluate which material should be better than other for a high frequency, high power application. But now if we consider how much power it can deliver, let's take a case where we make a class A power amplifier with a high frequency MOSFET. And for a class A power amplifier, the maximum power output, linear power output can be defined by this equation. Again, the detail of the derivation. Here we can see that the maximum power output at a given frequency is a square, has a square dependence on the Johnson's figure of merit. And if we fix the power gain GP and the input impedance, if we can maximize the Johnson's figure of merit, we should get a higher power at a given frequency. Now again, if you look at our material options, the common materials for high frequency, high frequency application is silicon and gallium arsenide. Gallium arsenide is popular for high frequency because it has a much higher mobility than silicon. And in this plot, in the x-axis, we have the frequency in gigahertz, and the y-axis, we have the output, linear output power of a class A power amplifier in watt per millimeter. And I'm showing here the desired corner is on the top right, where we have the highest power at higher frequency. So again, we're actually, silicon and gallium arsenide kind of in the same range because they have a similar band gap and similar critical electric field. Now, if you are to replace this transistor with a wider bandgap semiconductor, again, I'm talking about silicon carbide and gallium nitride, we can see that we can again get orders of magnitude improvement at a given frequency, how much power it can deliver in a power amplifier, or at a given power, how much higher frequency it can operate. Looking at this figure of merit, just from a material perspective, we are excited that if we can replace this existing silicon or gallium arsenide technologies for power and high frequency application with a wider bandgap material such as gallium nitride or silicon carbide, we can enable many new applications that has never possible before. So with this, I would like to switch a gear a little bit and give a specific example of a wider bandgap material of my choice where I work this, and talk about some of the things we have been doing to enable this. I'd like to talk about the gallium nitride. So to introduce the gallium nitride, it's a compound semiconductor, and it's called a polar semiconductor, which means the crystal structure of the gallium nitride is not symmetric. So there is if you look at the unit cell of the gallium nitride from really unit cell point of view, there is a built-in charge dipole of this nature of the. And this is also a piezoelectric material. And unlike silicon dioxide, it's not a cubic structure, it's a hexagonal structure, as we can see from the top view image here. And it's a so-called Woodside, forms of Woodside lattice where we have the gallium and nitrogen atoms in the structure. So this piezoelectricity or this polar semiconductor nature gives some unique advantage that no other semiconductor material actually possesses. So here on the left, we're showing a typical how a gallium nitride heterostructure looks like. So we have this grayish region is say 1 to 2 micrometer thick gallium nitride grown, and if we grow a very thin layer, say 20 nanometer of a ternary alloy, which is aluminum gallium nitride. It's a combination between gallium nitride and aluminum nitride. So both of these materials are piezoelectric, and they have a different lattice constant. So when we grow a thin film on a thick gallium nitride, there is a tensile stress forms at the interface. So because of this tensile stress, there is a built-in piezoelectricity, and there's, I also already said, there is also spontaneous polarization because of their crystalline nature. So what happens at the interface, we form a two-dimensional electron gas of or very high concentration of mobile carriers, which makes these devices really unique. So on the right-hand side, I'm showing the energy band diagram along this z-axis. So we have nickel on the left, and we have this aluminum gallium nitride and the gallium nitride. And as we can see, because of this piezoelectricity and the spontaneous polarization, a quantum well has been formed here, right at the interface, where we have a very high mobility carrier concentration that can act as a channel. So this is very unique for this material system because in any other material, if you want to form a channel, we either have to dope or apply a voltage to invert the semiconductor itself to form a carrier channel. But because of this unique crystal structure nature, this gallium nitride material, when we grow just heterostructure, it forms a channel by definition, which is a high carrier density and very high mobility. It's a very attractive option for high frequency and high power electronics. And this, the transistor built on this, using this structure is called a high electron mobility transistor, or HEMT. So it has been a revolution on the use of this gallium nitride lateral power FETs or high electron mobility transistor over last 20 years or so. And in this, here we're showing that a lot of different application that has been enabled over the year. Bidirectional IC, different kind of IC and the power modules, and it's just going on and taking over the market for the power. One thing I would like to draw attention here, most of this application, the voltage is limited to 650 volt with this lateral structure that I showed in the previous slide. So there are a lot of, there is still a room for improvement to go beyond this voltage or voltage limit, the gallium nitride, which I'm going to address in the next few slides. So the gallium nitride lateral power FETs enjoyed a tremendous success, but there are some drawbacks. So here on the left, we have a typical structure of a gallium nitride lateral HEMTs, the source on the left, and the gate on the middle, and the drain on the right. Since it's a power device, we have a long drift region, and the device is asymmetric, blocking voltage. So there are the major limitation of this HEMTs is first, it's very difficult to increase the current beyond 50 amps in these devices, because one way to increase the current is increase the area of the device, which in turn actually increases the footprint of the device, which means the device will become bulky if you try to supply very high current. And the second, the most intriguing problem here is basically when we operate at such a high power, we also generate a lot of heat in the device, and that's detrimental. And since these lateral devices, the channel is right at the surface, if you try to plot the heat map of the device, it kind of looks like this. So what it means from this plot is the heat is really concentrated near the surface, near the gate region, and we have this bulk of the substrate, which we don't use the heat. So this become an operating bottleneck for this device in a high power. Second biggest challenge is the electric field non-uniformity. Again, it's a surface device, and under high voltage condition, there is a peak electric field at the surface that causes the issue with the device reliability. And the last point, which was pretty obvious, if you want to increase the blocking voltage of the device, the only way to do it basically increase the distance between gate and drain. So if you want to increase the distance between gate and drain, again, our chip footprint becomes very large, and which we don't want as a consumer when we try to buy a, say, laptop adapter. We always wanted to buy the one with the smallest footprint, which we can carry. So it's not very attractive to build a very large voltage devices with lateral, which have a lateral geometry. So which brings us to my next part of the talk, where we're going to do what, in our group, what we are focusing on to solve these problems of the gallium nitride lateral HEMTs. So in the last probably 5 years, there's a new revolution in the gallium nitride power electronics, where people are trying to explore a novel kind of devices or vertical gallium nitride transistor for high power application. So there are predominantly two structures that can be found in the literature. One is called on the left, which is CAVIT, current aperture vertical electron transistor, and the second one is called trench MOSFET. The advantages are fairly obvious. So now, since the current conduction is in the vertical direction, where we have a drain at the bottom and source on the top, we can keep this device footprint same, but just by increasing the thickness of the device, we can support a higher PV or blocking voltage. And since the current is flowing in the vertical direction, the heat and the electric field are well distributed in the vertical direction, and there is no peak on the surface, and it should have a better reliability than the lateral devices. Just to explain how this device kind of work, so as we see, we have a drain at the bottom underneath the surface, and then we have this is N minus GaN, which is the drift region. And on the top, we have source and gate, and here is the channel region. So the main challenge of these devices is this P-type regions. That's called the current blocking layer. This layers has to be introduced so that the device can turn off. It's just like similar to the silicon power MOSFETs I showed a few slides ago. But there is a specific problem with this technology. For gallium nitride, although they have these devices enjoy tremendous success, people have demonstrated 1.5 kilovolt, 2.2 million centimeter square device in the both structure and up to 10 amps current from a single device. Major challenge is this the growth of this P-type layer. So if you look at from the material grower point of view, the way this device is being grown is someone grows a thick N- GaN here up to this point, and then they have to grow the P-type region and then do some H and regrow the N region on top. This is what they, people typically call regrowth. So you have to put in the growth chamber twice. That makes this device fabrication extremely expensive and challenging, and that comes with the additional many other problems. The second problem, which is fundamental to this gallium nitride technology, is the P-type doping. Unlike silicon, gallium nitride doesn't have an efficient P-type doping mechanism. So getting a desired doping, P-type doping in gallium nitride is very challenging, and that's very inefficient. So if you want to make a technology in gallium nitride successful, it's most likely has to do with this structure that doesn't have a P-type region or regrowth. So toward this goal, our group a few years ago came up with a unique structure where we don't have these two problems. Again, this is the schematic structure of the schematic diagram of the structure we are using. So we have, again, drain in the bottom, the source on the top. The way we make these devices, we define a in-shape geometry in the channel, and we put the gate dielectric and gate on the sidewall of the channel. In this way, we use the gating depletion mechanism of the between gate and semiconductor channel to turn on or turn off the device, and the current flows across the sidewall of the device. So as we can see, there is no P-type region present in this device, and there is no need for the regrowth. That makes these devices very attractive for fabrication and commercialization. And we found from some simple calculation that we can also control the threshold voltage of this device by just adjusting the width of the fin in these devices. This device operates in the accumulation mode of operation, where we apply gate bias, accumulate carriers in the sidewall. So following this concept, our group has been working on this for a while. So here I'm showing a typical cross section of the fabric group. So we can see the gallium nitride fin here, which is in this particular plot, 20 nanometer of width. And we have gate on the sidewall of the device, not showing the drain. Drain is somewhere in the bottom. And we can see this metal, which is the source on the top. And in between source and gate, we have some insulation, the silicon dioxide. And for this particular case, the gate length is about 730 nanometer. And we just don't have a single fin in these devices. If you look at this schematic diagram, this kind of looks like this. We have the drain at the bottom, then we have a 300 to 400 micrometer gallium nitride substrate, the drift region about 6 to 10 micron, and this hundreds of fin in parallel to support the current flow of this device. So these devices turned out to be very successful in the early days of operation. And our group has shown that these devices can, like a very good transistor, with a subthreshold swing as 77 millivolt per decade, which is very close to 60 millivolt per decade, the ideal limit, and very large on-off ratio of 10 to the power 10, and very low specific on resistance. And we have also shown that the devices can operate up to 800 to 1200 volt breakdown, and a single device can support 10 amps of current and which is the to date, the smallest device area in all 10 amps gallium nitride transistor demonstrated in literature. So this is all very great. So we get a good device, we have good performance. Why don't we start commercialization? So here comes the second part of being an engineer. When we get a good performance, we'll also have to think about the economy and cost, make it viable for things in the market. So a primary challenge for this gallium nitride technology is the wafer. In silicon technology today, they use 12-inch diameter wafers for mass fabrication. So having a larger diameter helps to maximize the yield and minimize the cost. But if we try to compare what kind of substrate we can have for gallium nitride, the devices I showed in the previous slides are fabricated on pure gallium nitride substrate, or so-called GaN on GaN. And as we can see, the wafer diameter for this device is 2 to 4 inches today. And the wafer cost is close to $100 per centimeter square. But this device, since it's a gallium nitride on gallium nitride, the quality is very high, and we can grow thick gallium nitride layers to support larger blocking voltage. So we have second option. We can also grow gallium nitride on silicon. And as of today, we can do 8-inch gallium nitride on silicon at a very low cost, almost 2 orders of magnitude lower cost compared to the GaN on GaN. However, we're trying to grow gallium nitride on a different semiconductor. Here comes a lot of materials related issue. And as it happens to be that if we grow gallium nitride on silicon, we have a lot of defect that lowers the device performance, and we cannot grow thick gallium nitride that's required for higher blocking voltage. So here, as an example, I'm showing the cross-section TEM image of a gallium nitride grown on silicon from literature. So on the bottom, we have this silicon wafer, and gallium nitride is actually being grown at a very high temperature, 800 C. And when we grow at a 1000 C, so when you grow at a high temperature, we also need to consider that different materials had different coefficient of thermal expansion. So there need to be, since they have a different lattice constant and different coefficient of thermal expansion, so there has to, we need to put something in between to make this transition for this growth to happen. So as a result of this, we have to include aluminum materials like aluminum nitride and aluminum gallium nitride in between silicon and gallium nitride. So this turns out to be very defective, and as we can see, some of these defects are visible in this TEM. And if we try to grow a thick GaN layer, say more than 5 micron, this gallium nitride starts to crack and starts showing defect, which is not good when we are trying to make a power device which transport in a vertical direction. It has been a major challenge over the last decade or so to commercialize these power devices on gallium nitride. So to explain this problem a little bit more, so here we have the temperature on the x-axis. On the y-axis, we have a so-called CTE, or coefficient of thermal mismatch of different gallium nitride substrate. The red line with the dotted points here, and the data for the silicon. And here, the blue lines, that's the gallium nitride. So we see that there is a large difference of CTE, which will cause the device to crack when we try to grow thick epi on it. So this, there is a company, Chromis, they came up with a proprietary technology where instead of directly make it on silicon, they make the substrate of polycrystalline aluminum nitride. And as we can see, the coefficient of thermal mismatch between polycrystalline aluminum nitride and gallium nitride is minimal, and that their proprietary technology can enable very thick gallium nitride growth on silicon substrates. Right hand side, we have one of the TM courtesy of Toshiba, where we have the silicon substrate, and then their so-called engineered layers, the technology, aluminum nitride core, and some and then we can see there's very nice, clean, crack-free 30 micron thickness, thick of gallium nitride grown in this substrate. And as it happens to be, this also can be grown in a 8 to 12 inch wafer scale. So we got pretty excited when we came to know about this technology. And recently we started working in this company, with this company in collaboration. They are giving us the substrate, and we tried to fabricate this particle power FinFET on this substrate. And we're starting to get very good results from our first try. So we recently fabricated our first devices, and if we try to see where we are, and on the right-hand side, we have this plot where we have the EOT of the gate dielectric, and y-axis we have the maximum current capability. And these are the other devices present in the literature where people fabricated vertical GaN transistor on silicon-like substrate. We found that our devices are performing pretty well, and that's really shows a promising performance among the GaN on silicon vertical transistor for commercialization application in future. So next, I'll give a brief example, very brief introduction of a novel device that can also enable high frequency, high power with the gallium nitride. So as I mentioned earlier in my presentation, that to increase the frequency, the primary goal is to minimize the transit time of the carrier between source and drain. Happens to be for MOSFET, it's very difficult to minimize the transit time between source and drain in a standard fashion. So to overcome this problem, I'm introducing a novel device concept that has been there for literature, which is called the hot electron transistor. It's a 3-terminal device where we have emitter like a BJT, and base, and the collector. And in between base and emitter and base, there is a tunnel barrier where by means of quantum mechanical tunneling, electrons are being injected from emitter to the base. And to control the carrier flow between base and collector, there is a barrier between, there is also insulating barrier. So current flows in a vertical direction, and it's a unipolar and transport of a majority hot carrier. So increase the frequency. One idea was, why don't we just thin down this base thickness, and that should give us the highest possible frequency, because the base thickness limits the transit time of the carrier. So people have tried over the years many different materials, and including gallium nitrides. So what we proposed a few years ago is basically, why don't we use single atomic layer base between these insulating layers? It has to be the single atomic layer graphene can be an attractive option. So I'll just keep it brief. We fabricated some of the devices, and here we are showing a cross-section team image of the world's smallest transistor in terms of the source to drain distance. We have the gallium nitride substrate, a 5 nanometer thick of aluminum nitride tunnel barrier, which is the origin here, a single atomic layer graphene, which is 0.7 angstrom thick, and 2 to 3 nanometer thick tungsten disulfide collector layer. So the whole transistor where the transport happens is less than 10 nanometer thick. So this is one of the kind of novel devices that can be enabled when we combine many new different materials. And potentially these devices can support very high current and high frequency and high power. Before ending the talk, I'll give a brief outlook since I have shown that the gallium nitride can be a very promising option for high frequency, high power electronics. So what's next, and what we should look into the future if we are to do research in this field? So as it happens to be, the silicon carbide and gallium nitride are not only the wide bandgap material. There is a new family of semiconductors, so-called ultra wide bandgap material, beta gallium oxide, aluminum nitride, or even diamond, where we have a band gap ranging from 4.9 to 6.2 electron volt. They also have a very decent mobility and other parameters. And everyone in the community is pretty excited, and there is a lot of effort going on to make power and high power, high frequency devices based on these new materials to enable even higher more capability. For example, if you want to have a 10 kilovolt breakdown or blocking voltage, silicon, because of this narrower band gap, would require a 1000 micrometer thick drift. Now, if we move to gallium nitride, because of its wider band gap, to support the same voltage, we'll need only 100 micrometer thick drift region. Now, if we can go into the diamond and keep it to support the same voltage, we will only need 20 micrometer thick of drift region. So this kind of sums up that why these ultra wide bandgap materials are very promising and why the community is so excited. So if you go into the literature, you can find there are a lot of exciting works going on, and there's a lot of effort around the world. So I believe this is the diamond and aluminum nitride, the next frontier for high power applications in this area. Again, if you look at the high frequency, so here I'm the figure of merit again. As we can see, we have already seen the silicon carbide and gallium nitride can enable some high voltage with a low on resistance. But these new materials here, we say that we are we can also improve another 5 to 10 times in enhancement in the breakdown voltage and the on resistance by introducing new materials. But these materials are new. There are a lot of materials related challenges that needs to be solved before they can come into application. And as I mentioned, the substrate is one of the major economic bottleneck for this commercialization. These days, the diamond and aluminum nitride, the substrates are really small. So there will be also another new round of challenges with those. And again, if you want to look at the high frequency, high power applications with the Johnson's figure of merit and the maximum linear power, we see that introducing materials like diamond and aluminum nitride can enable a new range of application beyond the capability of gallium nitride or silicon carbide. So everyone is pretty excited about these new materials, and there are a lot of efforts going on around the world. So this is where I'm about to end. Before ending the talk, I'll also like to briefly introduce some of my work I have done in my PhD, which is not related to the core theme of the talk. So there is another family of material I think a lot of people are familiar about. It's called so-called atomically thin two-dimensional materials, where I work with the very ultra short channel transistors, where we demonstrate transistor with a channel length down to 7.5 nanometer. We work on heterojunction tunnel FETs with a low power application. I mentioned about the transistor already. And we also worked on the novel ferroelectric materials like doped hafnium oxide and demonstrated negative capacitance FETs with the multi-SFET channel. And we're also happy to answer any question in these fields if anyone is interested.
Firstly, thank you so much for the really great talk. I think we have a lot of questions already in the chat box. So I would like to go through them chronologically. First question was asked by Ramit Orko. So if you could unmute yourself and introduce yourself and ask the question.
Hello, my name is Ramit Orko. I'm from Bangladesh and I'm a student. I'm right now studying at Daffodil International University on subject Tripoli. So my question was about the materials that you were talking about, the semiconductor, and you replaced with gallium nitride. So my question was, can we replace the whole semiconductor with carbon nanotube technology so that the thermal efficiency can be more improved here?
So, I mean, this is a very good question. Yeah, there have been a lot of effort going on in the carbon nanotube for different applications. So as I said, the application space I'm talking about today is high power and high frequency. So one of the critical requirement for a new material to do this kind of application is the energy band gap. And if you look at the energy band gap of the carbon nanotube, I think it's probably close to, I mean, maximum probably you can get about 1 electron volt, which is close to silicon. So carbon nanotube are exciting for different kind of application like low power or very scale transistor, but probably high power application, it may not be the best. I mean, it may not give you any, I mean, a very
Like
significant advantage.
sorry, sir, sorry to interrupt you. Like the ARM architecture and the x86 architecture, like this, the power consumptions and the power output system capability. That is the point.
Yeah, so yeah, I mean, for microprocessors, carbon nanotube would be excellent choice. But the applications we are talking about is basically not in the microprocessor. We're talking about the operating voltage that ranges from 100 to 1000 volts. So when you talk about the microprocessor, what's the highest voltage level you are operating with?
Probably 15.
Probably 15 volt. Yeah, in that range, carbon nanotube would be an excellent choice, no doubt about that. But when you're going beyond 15 volt, we're talking about a power converter, DC to DC converter or DC to AC converter, or in an electric vehicle or in a data center where we need to support a voltage ranging from 100 to 1000 volt. At this particular voltage range, probably carbon nanotube is difficult to deal with because of the same reason why we cannot use silicon there, because of their band gap is narrower. But for the application you mentioned, yeah, carbon nanotube is an excellent choice there.
Thank you, sir.
Thank you very much. I think the next question is from Muntasir Mahdi. If you could similarly introduce yourself and ask the question.
Assalamu alaikum, sir. I'm Muntasir Mahdi, currently working as a junior lecturer at University of Science and Technology, Chittagong, in the Department of Triple. The question was about you have shown the gallium nitride HEMT device, and the temperature was concentrated in a particular area. Is it possible to use any kind of high thermal conductivity as a substrate of a gallium nitride device?
That's an excellent question. Yeah, actually, smart people like you also thought about that already. So as it happens to be, I think if you look at the material, one of the material of choice is actually diamond, which has a very high thermal conductivity. So there have been also a lot of effort going on where in the substrate, people are trying to introduce diamond to dissipate the heat there. So yeah, there have been research already on this direction. People are trying to use a high thermal conductivity material to solve this heat dissipation issue. And it helps to some extent, but again, it also has its own limitation. When you introduce in different materials in the substrate, you also have a thermal boundary to deal with, which makes design a little bit complicated. But that's a very smart way to go about this problem. Thank you.
Thank you very much. Next question is asked by Faisal Nayan. If you could similarly introduce yourself and ask the question.
Hello, assalamu alaikum, sir. I am Faisal Nayan, currently working as a faculty member of Assam University. Actually, I have a same question as Orko. What is the prospect of carbon nanotube in the as a wide band gap material? As we know that by changing the chirality of the carbon nanotube, we can operate the carbon nanotube as a metal as well as the semiconducting material. Is it possible to increase its band gap by changing its chirality? Thank you, sir.
So I mean, again, I would say the same answer. So for some particular applications, the 10 to 15 volt, carbon nanotube would be excellent choice. But, again, if you go back to this table here, as we can see that if you have a band gap of close to 1 electron volt, we cannot, it would be same as silicon, and it cannot enable any application beyond, say, 100 to a few hundred volts, even in the best condition. So if you want to enable application that requires more than 100 volts, probably carbon nanotube is not the best choice to go about there. Thank you.
Thank you very much. Next question is from Mohammad Mohiuddin. I think you had a couple of questions, so please go ahead and ask the questions. I don't know if you can hear me. It's still muted. So I'll just go to the next question. It's from Dr. Tasnia Hussain. So if you could introduce yourself and ask the question.
Okay. Listening to me?
Yes.
Okay, sorry, it says my wife's ID. Anyway, I just want to know actually how about gallium nitride on silicon, because if you want to grow thick gallium nitride on silicon, if you need to grow, then silicon would be much cheaper. On the other hand, if you use diamond substrate or other gallium nitride substrate, then it would be costly. So what would be the price of those devices people will get? And another issue is when you grow thick layer, about the thermal management, and because compared to your thin layer, let's say 20 micron thick on diamond.
If you could also introduce yourself.
Yeah, sorry, I'm from Dhaka Institute. Dhaka Institute Department.
Okay, so I'll just point back to this slide again. So yeah, I mean, everyone wants to grow semiconductor, make semiconductor devices in silicon because we have existing foundry facility and $1 billion of industry there. So if anything we can make on silicon, that would be cheap, scalable, and ready to commercialize. But I think you already kind of answered the question. First is it's very difficult to grow, avoid defects when we're trying to grow material on a different substrate. For example, if you try to grow gallium nitride on silicon, it's very difficult to avoid defects because of the difference in the lattice parameter, difference of the coefficient of thermal expansion, which also creates a problem with the thermal management. So that's why, you can see if you look at the state of the art gallium nitride from silicon.
Just one comment from your presentation. The Toshiba, they did grow 30 micron on silicon. They use silicon nitride treatment and they did something. Using these techniques, they can manage to grow 30 micron crack free, it seems.
Yeah.
So in that case, silicon gallium nitride on silicon should get the market, isn't it?
If you're talking about this kind of, we call it engineered substrate because it's not directly, there is silicon, but they have to put some other engineering in between. Yeah, that's the whole point that why we're trying to do this. So if you want to make this technology commercially viable or successful, we have to do it on silicon. There's no other way. We cannot use on gallium nitride substrate. That's very costly. So maybe for applications where people don't care about the cost, those would be the options to go. But if you want to reach the consumer market, it has to be done on silicon. And yeah, this is a very promising first step. That's why we are working with them and trying to understand that the material is crack free. How does the device performance is different from the gallium nitride substrate? There are actually, this is an ongoing research. So we are still making devices, trying to understand the materials and device limitations. But we are very hopeful that this would be the way to go in coming days to commercialize GaN. Yeah, you are right, absolutely right about that.
How about the thermal management about thin gallium nitride or diamond?
Thermal management, if it's a pure gallium nitride, the thermal management in a vertical device is actually much more easier than lateral device because you have the whole volume to dissipate the heat. And this is also, people have shown from experimental data and simulations. But if it's on diamond, there are some exciting results, to be honest. But again, if you have two different material, you have a thermal boundary there. So that boundary has to be dealt smartly. So there are issues, but there are also promises there.
Thank you very much.
Thank you for the question. I think Dr. M. Tansir Ali has a comment or question. So Dr. Tansir is the Vice Chair of YP Bangladesh. If you could go ahead and ask what you wanted to say.
Thank you very much, sir. I'm Dr. Tansir from AIB. I'm doing some research on nanoelectronics as well. My question is that about the simulation tool. We use Silvaco or TCAT simulation tools, but for the materials, we use Silvaco type simulation tools. But for device simulation, we kind of guess from the IV characteristics and just make the device. But there is any easier translation software which can automatically convert the codes? Do you have anything in like that? Or how do you do that? You simulate the device in a TCAT simulation tool, Silvaco, like that, and how you convert the simulation tool to a device model?
I'm not. I mean, if I understand that correctly, so for us, we also use like the same software what you are using, like Silvaco or Centaurus for simulating these devices. So we try to simulate from the first principle, taking the material parameters from the literature, and then when we measure the devices in the lab, fabricate and measure, so we try to calibrate our simulation based on our experimental data. So, and
no, I'm saying that say you design a diode or a transistor, and then you want to implement in a system or a circuit level.
Oh, I see. Oh, I see what you're saying. So, okay. So for that, I think Silvaco or Centaurus is a device simulation tool. So once we have these device results, we try to convert it to a compact model. For example, our group particularly use a compact model called MIT Virtual Source Model. I think you can find it from the Nano Hub. The model is already there. So if you can convert the device results, the experimental results to this compact model, then you can use any circuit simulator like Cadence or ADS to simulate the circuit and system level performances. So this is how we typically do. We do fabricate the device, simulate in Silvaco or Centaurus, calibrate it, get the accurate model, and then convert it to the compact model using MIT Virtual Source Model. And then we incorporate this compact model into a circuit simulator in a Cadence or ADS to simulate the system level performances.
Okay, so the website you are saying is that the nanohub.org?
Yeah, you can just search the MIT Virtual Source Model and you'll find all the models and codes there.
Okay, thank you very much. I'm just, we have designed some devices, but we are stuck how to translate into circuit level design. So thank you very much.
Yeah, no problem.
Thank you very much, Dr. Tansir. I think the next question is from Dr. Fahim Rahman. He's also an alumni from BUET EEE and currently working as a research assistant professor in the University of Florida. So Dr. Rahman, if you could go ahead and ask the question.
Thanks, Sajid, for the introduction. Dr. Zubair, awesome talk. I was actually planning to keep myself muted because people are working outside in garden and everything, so there might be some noise. My question was basically more like the commercialization of the materials, which in some level is already answered throughout the discussion and based on some of the previous questions. But I can repeat myself again. So my question was like, how are the front runner silicon fabs like TSMC, Intel, or Global Foundries investing in such emerging materials? Or do you envision, or do you need to rely on some other niche type of fabs to build these devices?
So that's an excellent question. So I think gallium nitride is not really that new. Basically, the gallium nitride people started to build this fabrication facility for gallium nitride and silicon carbide for over the last 20 years. The main success from gallium nitride came from their success with the LEDs, the blue LEDs. So I think by now, all the major foundries, they have some sort of gallium nitride fabrication capabilities in-house. I know that Intel has some, TSMC has a very big program on fabricating these gallium nitride devices. I think probably GlobalFoundries also have. And in addition to that, there are other companies, they're also investing heavily and this TSMC, Intel, and GlobalFoundries was predominantly microprocessor industry. So they were focused on the low voltage devices. But there are a few companies like Texas Instrument, Analog Devices, and many other companies. They are predominantly focused on high power and high frequency electronics. They have also their dedicated fabrication facilities these days for this new wide bandgap material. And of course, there are some companies just dedicated on gallium nitride electronics. There is a company even from MIT, Cambridge Electronics. They are a startup trying to build a gallium nitride technology based on the lateral devices. Then there is a EPC. Then they're also trying to build lateral GaN HEMTs technology. They have their own fab, I think. And for vertical gallium nitride transistor, there was a company started like 3 years ago. It's called NextGen. They have their own dedicated facility for fabrication of the gallium nitride. So the bottom line is, if it's based on the gallium nitride substrate, yeah, we need a dedicated processing facility to process those wafer. And some of the old technologies with gallium nitride are not compatible with the silicon foundry. For example, in the silicon foundry, they don't allow any kind of gold processing. It's a killer for some silicon devices. But if you look at the gallium nitride HEMTs, the contacts has some sorts of gold in it. So to solve that problem, people have moved to gold-free contacts and trying to make this gallium nitride processing CMOS compatible. And after some effort, now almost all the companies have some sort of gallium nitride fabrication facility that can go side by side with their silicon CMOS.
Thank you very, very much. Yeah, that was an excellent answer. And obviously, with the gallium nitride, we actually have achieved some level of maturity. May not be necessarily up to like CMOS for traditional microprocessor design, but gallium nitride itself has its own maturity. I was actually more looking forward to more emerging ones where you have carbon and so especially new vertical structures. And if I consider correctly, probably GlobalFoundries also use some gallium nitride architecture for, I might be mistaken, but for microprocessor design as well, for very ultra low power implementation, just to make sure that there is not enough leakage, because it's ultra bandwidth, but it's not necessarily a traditional MOSFET structure. But yeah, it's actually really good that these frontrunners have such kind of capabilities side by side, because most of the cases, the commercialization of the technology dominates the force of research, and also what would be our upcoming futuristic microelectronic devices should look like, right? But that was an excellent answer. Thank you. And we'll definitely talk more when you visit Florida next time.
Yeah, absolutely. Thank you. It's an excellent question. Yeah.
Thank thank you very much, Fahim, for the question. So next question is from Mohammad Aminul Haq Chaudhry. If you could introduce yourself and ask your question.
Assalamu alaikum, sir. I am Aminul Haq Chaudhry from Tripoli Department, University of Dhaka. Thank you so much for this excellent talk. I have actually two questions, but the first question was about using aluminum materials to solve the mismatch of thermal coefficient of expansion on gallium nitride on silicon. You have already answered that question very nicely. So my another question was about hot electron transistor that you showed. So in that you showed that there is a quantum tunneling between emitter and the base. Can you please briefly explain what's the use of quantum tunneling in this section? Thank you so much.
Yeah, thank you. That is an excellent question. So for a typical MOSFET, when we inject carrier from source to gate, is basically over the barrier thermionic emission. What happens in the thermionic emission is the electrons are very close to the conduction band. So when it reaches the channel, it also, there's a possibility that it gets scattered. So now, instead of doing that, if we use a quantum tunneling and try to inject from a really high energy, so that when the carrier reaches from emitter to the base, the energy of the electron is much higher than the Fermi level of the base. So this is so-called hot electron because its energy is higher, the temperature should be hot. So when the energy of the injected electron is much higher than the Fermi level of the base, there's a minimal possibility of scattering with the already existing carriers in the base. So when there is no scattering, we can actually envision a ballistic scattering field transport. And as we know that if we have a ballistic transport, it has to be really fast. The idea of this device was to make it a really fast transistor and enable ballistic transport. And as it happens to be making a ballistic transistor with the over the barrier thermionic emission is very challenging because of all the scattering, and which is typically called cold electrons. And that was the motivation to use quantum tunneling.
Right.
Does that answer your question?
Thank you so much, sir.
Okay, thank you so much. And last question in the chat box is Shakhawat Hussain. You can unmute yourself and introduce yourself before asking the question. And also, if you guys have any other questions, please feel free to use the chat box and ask more questions. Shakhawat, the floor is yours. Okay, I don't think he's right now in the meeting. So I'm going to go ahead and ask the question that he wanted to ask. So how to make the contacts to the gate in your fin structure. So what kind of material do you use for the contacts? I think that's the question.
So yeah, I think that's an excellent question. So that's why I brought up this slide. So this is a vertical device. So if from the left SM image, we see that the gates are on the sidewall of the fins. And typically we use a metal that can be easily etched. For example, we use molybdenum or tungsten for our gate metal. And to make the contacts, I think we have to look at the diagram on the right-hand side. So we have hundreds of these fin-like geometries in parallel, and the gates goes on the sidewall. But at the end of the device, we use there is an extension of the gate metal where we actually land our probes to connect the device. So yeah, the material is something molybdenum or tungsten, but to contact, we'll use an extension gate pad that's designed on that's already designed in our mask.
All right, thank you very much for the nice answer. So before we want to take a group photo with the speaker. So everyone, if you're comfortable, please go ahead and turn on your webcams. And while you do that, I also want to share my screen quickly. So This is a virtual certificate that I want to present to Dr. Zubair for his excellent presentation. And this is by far the most widely attended Meet the Young Professional talk. I'm sure all of you who are still here, you're really excited about the topic and the really nice presentation by Dr. Zubair. So we really thank him for giving this nice talk, and I'll email it to him after today's session. So
Thank you.
also, I want to let everyone know, I think there were at least 3 or 4 people who either messaged me personally or wrote in the chat box. So they're really interested in getting the speaker certificate for today's event. So, sorry, not the speaker certificate, the recording of the session. So with Dr. Zubair's permission, we would first record this session and upload it to YouTube in private. And then if he agrees to make it public, we could then share it with everyone in our YouTube channel. So please go ahead and subscribe there in our YouTube channel. Okay, there is one last question from Muntasir Mahdi. Muntasir, if you can go ahead and ask the question.
Sir, assalamu alaikum, sir. I've already introduced myself in my first question. My second question was, I was wondering about the transmission electron microscope image that you have shown here. I think this is a cross-section image, right?
Yeah,
Sir,
you're right.
Sir, as far as I know, we need to have a thin structure to get the TEM image. So how did you take this this cross-section with a thin structure for the TEM image?
First to clarify, I don't do TEM. So we have material science colleagues who are really have excellent capabilities to do this kind of experiment. So when we need help, we just reach out to them and they solve our problem. So yeah, but to answer that, I think the way, if I understand correctly, they cut a small cross section with a focus ion beam, and then with the gallium ion, they actually thin it down to take the image. So you are right, you cannot do TM with the big samples, but they have their nice tricks to make it thin, and whether we can see it in the under microscope. But yeah, I have never done TM myself, so I'm sorry, yeah.
Thank you, sir.
Thank you for the nice answer. So now I'm trying to take the group photo. So please go ahead and turn on your webcams if you're comfortable, and look at the camera and smile. Great. Thank you so much for everyone. So this was the end of our today's Meet the Young Professional series talk. On next Saturday, we are hoping to get Dr. Himadri Shekhar De. So he works in the industry, semiconductor industry, and he works in one of the largest manufacturers of memory devices, Micron Technologies. So he is going to be talking about his experience in working in the fabrication facilities and how the career spans out there. So all of you are welcome to join our session on this coming Saturday. And with this, I would like to thank everyone for coming to this event, and thank again Dr. Zubair for his brilliant talk, and hopefully we would have him again in IEEE events in the future.
Thank you for the invitation, and it was very nice to meet all of you. Thank you.
Thank you.